welcome back. In this video, we'll take a look at some recursive definitions and structural induction. So far, we've come through weak induction, strong induction, and now we're taking a look at recursive definitions and structural induction. So this is applying the principle of induction to functions, sets, and other types of structures. So we'll start by taking a look at how this applies to functions. We'll look at recursive sets, and then some other recursive structures that you might not have thought of. And finally, we'll take a look at a CS connection, how this applies to linked lists and binary trees. First, we'll start off with recursive functions. And these are functions that you've already been making use of without realizing it. Recursive functions can be inductively defined. So this is an example of an inductive definition of a function, and it looks a lot like the induction steps that we've taken so far. So there's a basis step where we specify the value of the function at 0, and that is our term f of 0. The recursive step is to give a rule for the value of f of k, the function at integer k, based on the values that came before it. So when I give a value for f of 1, it's going to be based on f of 0. So f of k is a function based on f of 0 through f of k minus 1. And it can look like many different things. So here are a few examples. The first example is one that you might recognize in a moment. F of 0 is set to 0, and f of 1 is set to 1. And for n greater than or equal to 2, f of n is defined by the values just before it. So it's the sum of f of n minus 1 and f of n minus 2. So what does that look like? Well, f of 2 is just the sum of f of 1 and f of 0, which is 1 plus 0, or 1. F of 3 is the sum of f of 2 and f of 1, which is 1 plus 1, or 2. F of 4 is the sum of f of 3 and f of 2, or 2 plus 1, which is equal to 3. And f of 5 is the sum of f of 4 and f of 3, which is equal to 3 plus 2, or 5. And so we can play this out, and we can look at the values of f of 6, f of 7, f of 8, f of 9. And what we see is this is going to be repetitively the sum of the two numbers that came before it. So this will be 5 plus 3, which is 8. This will be 8 plus 5, or 13. 13 plus 8, 21. 21 plus 13, or 34, and so on. And hopefully, this has started to look familiar. If we put them in a line, we see that 0, 1, 1, 2, 3, 5, 8, 13, 21, and 34. And this, of course, is the Fibonacci numbers. In our second example, we'll see that we have another recursive definition for a function, but this time it's not necessarily one that you've seen before. So f of 0 is set to 3. And for every n greater than 0, we see that f of n is defined as 2 times f of n minus 1 plus 3. So twice the number that came before it plus 3. So for f of 1, this is 2 times f of 0 plus 3, or 2 times 3 plus 3, which is 6 plus 3, or 9. F of 2 is twice f of 1 plus 3, and if you were a computer trying to figure this out, so think about what that means behind the scenes. You can write a method that's a recursive method, so a function that expects some argument, and this time we're going to pass it n, and if n is equal to 0, we're going to return 3. But if n is greater than 0, then we're going to return whatever the calculations 2 times f of n minus 1 plus 3 is. And that's the important point here, is that actually what happens is we keep calling this repetitively until we get down to our base case, f of 0. And then we finally have a solid value that doesn't rely on any other information. And so what actually happens is we know that this is that f of 2, that we could stick in a 9 for f of 1. So that's 2 times 9 plus 3. But really what's happening is that this becomes 2 times the value of f of 1, which is 2 times f of 0 plus 3, all plus 3. And so it resolves in that fashion. And so that does become 2 times 9 plus 3, or 21. That interior step there, that's an important one to consider and understand, is that's the recursion. That's the inductive piece that it keeps happening. And so we can figure out that f of 3 is equal to 2 times f of 2 plus 3, which we know then calls twice f of 1, and f of 1 calls twice f of 0 plus 3, and so on. But for now, we'll just say we understand that happens, and this becomes 2 times 21 plus 3, which is 42 plus 3, or 45. F of 4 is 2 times f of 3, which is 2 times 45 plus 3, or 93. Example 3. In this example, we want to give a recursive definition for the factorial function, x factorial. And so we want to find f of x such that f of x is equal to x factorial. And we remember that x factorial is equal to the product of all the numbers from 1 to x. So it's 1 times 2 times 3, all the way up to times x. And so we see that when x is equal to 1, 1 factorial is equal to 1. And now we have to figure out how can we create a function that has a recursive definition where n is greater than or equal to 2. Well, let's look at what that means. So we know that f of n, we want this to be n factorial, which is the product from I equals 1 to n, which is the same as n times the product I equals 1 to n minus 1. But this is n times n minus 1 factorial. And that means f of n is equal to n times f of n minus 1. And so this gives us a recursive definition for this factorial function. In this last example of recursively defined functions, we want to give a recursive definition for summation. So in this case, we'll have a function, f of n, that's set to be the sum from k equals 0 to n of a sub k. And we know that this then becomes a sub 0 plus a sub 1 plus a sub 2, all the way out to a sub n. And so we want to define this recursively. So what is a sub 0? Well, that's just the sum from k equals 0 to 0 of a sub k, and that's just a sub 0. So our first step in defining this function is defining that base. F of 0 is equal to a sub 0. For anything bigger than that, we can note that this is the sum from 0 to n of a sub k, but that's the same as saying this is the same as a sub n plus the sum of k equals 0 to n minus 1 of a sub k. And that we can say is a sub n plus f of n minus 1. And that gives us that recursive piece that allows us to recursively define this function. But we can apply this induction principle and recursive definition to other things like sets. So how do we recursively define sets? Well, first we have to have a basis step, and that is we define an initial collection of elements. So we say that we've got these pieces X, Y, Z that are in the set, and then based on those, we give a rule for forming new elements based on those already known to be in the set. So we build the set from the sets that we initially put in there. Let's take a look at an example of a set. So initially we create a set and we say its initial collection of elements is the integer 0. And then we create a rule based on what's already in the set to recursively build out this set. And we say if X is in our set S, so this is the set S, then X plus 1 is in S. 0 is in S, so on that first step, I'm going to say, well, then 1 is in S. In the next iteration, I say if 0 is in S, 1 is in S. I'm only going to include unique elements, and 1 is in S, so 2 is in S. On the next step around, I say 0 is in S, 1 is in S, 2 is in S, so 1, 2, and 3 must be in S, and so on. And so I can keep following this out, and if I keep populating all of the new numbers that might be in there, you'll see that I'm slowly building out all the integers greater than or equal to 0. What if we change our basis step? If instead of beginning with 0 as our initial collection of elements, what if I started with 1? So I start from 1. Each of the iterations, I'm going to add, if I have a number x in S, then I'm going to make sure that x plus 1 is also there. So I'm going to build it out in the same way, but I end up with everything that I had before minus the 0. The 0 is no longer in there, and there's no way for it to be added because all I'm doing is starting with a positive number 1, and I'm adding 1 to all the elements that exist in the set. So in doing this, we created a different set. And so this recursive definition, the base and that inductive step, the recursive step, matter, and they create different sets. So what is this set? Can you identify this sequence? Well, this one is no longer including 0. In fact, we're building out the set of natural numbers. Let's take another look at an example. And here's a set. Let's see if we can identify it. So we start with the number 2 in S, and then we create a rule for building out the components of this set based on what's already there. So if X is in S and Y is in S, then X plus 1 is in S. So we see we've got 2 in there, so that means 2 plus 2 must be in there, but that's 4. And because now we see that 2 and 4 are in there, then 2 plus 2 is in there, 2 plus 4 is in there, 4 plus 2 is in there, and 4 plus 4 is in there. And 2 plus 2 is equal to 4, 4 plus 2 is equal to 2 plus 4 is equal to 6, 4 plus 4 is equal to 8, and so we end up with 2, 4, 6, 8. We can keep going. We see that now that 6 and 8 are in there, that means that 2 plus 6, or 6 plus 2, 8 is in there. It's already there, so we won't list it again. 8 plus 2 and 2 plus 8 are in there. That's 10. And also 6 plus 6 and 8 plus 8 are in there. And so we can continue going. But hopefully you'll see that we can eventually build out all of the even numbers And so this is a recursive definition to create the set of even numbers. How about this one? Now we're going to keep the base the same, but the recursive step is different. And so we'll create our set S. We're going to start with the same base, but this time, if we have two elements in the set, then the product of those elements is in there. Since 2 is in there, that means 2 times 2 is there, and that's 4. And now since we have 4 in there, that means that 2 times 4, which is the same as 4 times 2, which is 8, must also be in there. And now since 8 is in there, that means that 2 times 8 is in our set, and that is 16. And it also means that 4 times 8 must be in there, which is 32. And we can keep playing with this, but since we got the 16, we might as well see that 2 times 16 is in there, 4 times 16 is in there, and we have an 8, so 8 times 16 is in there. And if you play this out, that's 32, 64, and 128. Just to add a few more to the mix so we can start to see what we're getting. But what we're actually building out is the powers of 2. So this is a recursive definition to build a set that holds the powers of 2. Recursion can be applied to other things. So let's take a look at some recursively defined structures. And that might be different than you expect. So one recursive structure that you might not have thought of as a recursive structure is the set, which we'll represent as sigma star, of strings over a specific alphabet. So for instance, in the English alphabet, we've got a finite set of symbols, the letters A through Z, that we can create strings out of. And we'll call that set sigma star. There's a recursive element to developing the strings that can be created from a specific finite alphabet. So the basis step in this scenario is to first start with an empty string. So we let lambda be the empty string, a string that contains no symbols. And then the inductive step is to say, if you have something in our set, so we've got our set of strings sigma star, and we place lambda, the empty string, in it, we say over this finite alphabet, if you've got a y in your alphabet, then xy is in sigma star. It's one of the strings that can be built from this alphabet. So for instance, as an example, if we started with the alphabet 0, 1, well, what's in sigma star? In this case, we can have, so we have only lambda, the empty string, in our set of strings so far. But in our alphabet, we have both 0 and 1. And so y can take on 0 or 1. And so in here, we're going to get the only options on that first iteration are lambda 0 or lambda 1. But because lambda is the empty string, that means we're adding 0 and 1 to our set. On the next iteration, you'll see that we can reach 0, 1, or now we get the combinations 0, 0, 0, 1, 1, 0, and in fact 1, 1. And this continues. And this is how we can build up the set of binary numbers represented as strings. What if we want to show that the set of strings that we can create, sigma star, from a specific alphabet, sigma, in this case, we're letting that alphabet be that which contains the letters A and B. What if we want to show that it contains a specific element, AAB? So we know that we start off with a basis step that is the same. We let lambda be in our set of strings, sigma star. So the empty string is in there. and then we can build it up from there. So the way that we start is we say, well, we know that sigma is in alpha star. There it is. And we know that A is in our alphabet. But then lambda A must also be in the set of strings. And lambda A, because lambda is the empty string, is the same as A. A is in the set of strings that we can produce. The next step is to say, well, now I have A in my set of strings, and I know that A is still in the alphabet, and so AA must also be in that set of strings. Here's all we need now, because if AA is in there and B is in our alphabet, then we know that AAB is in the set of strings that we can produce. And there are other elements in there, many, many more, but we do know that AAB must be, because we followed it through that inductive step multiple times. We've been looking at recursively defined structures, and just like a recursive algorithm, a recursive structure is defined in terms of one or more base cases followed by one or more inductive cases. So structures that can be built up from smaller instances of the same structure can be defined recursively. They're recursive structures. Two examples of these that we see quite often in computer science are linked lists and binary trees. Let's take a look. A linked list is a data structure that's used quite commonly, and it's used to store a sequence of elements. Each element within the list is called a node. The real value of linked lists is something that you'll see in later courses focused on data structures. But for right now, we'll just take a quick look at what this looks like. So each element in the list is called a node, and each node is going to store data and a pointer to the rest of the list. And the rest of the list is also a linked list in its own right. So this is often represented something of the following form. So we'll have these nodes, and each node is going to hold some data. So for instance, if I had a linked list that was going to hold the letters of the alphabet in sequence, the first node is going to hold the data, which is a letter A, and then it's going to hold a pointer to the rest of the list. And the rest of the list is also a linked list, and the next element holds the letter B and a pointer to the letter C and a pointer to another node that holds the letter D and a pointer, and so on until we finally get to the letters Y and the letter Z. And the letter Z is the last letter in the alphabet. So the letter Z is the end of this linked list. And so instead of holding a pointer, this is going to hold the value null, which just represents the fact that the empty list follows. There's nothing that comes after that letter Z. What's important to note then is that this is a linked list, and this is a linked list, and as far as I go back, it's a linked list which is defined in terms of itself. So what that looks like, a linked list is either empty, known as null or the empty list, or it's something that holds a bit of data and another linked list. So this idea of a pointer, it's actually pointing to another linked list, which is what follows it. And that is a recursive definition. And this is a recursive structure. So for instance, if I were to create the following linked list, which has a subsequence of 5 elements from the Fibonacci series in it, 2, 3, 5, 8, 13, what we see is that this could be represented in the following way. It is the first a data followed by a linked list, which holds the data 3, followed by a linked list, which holds data 5, and a pointer to the linked list, which holds 8, and a pointer to the linked list, which holds 13, and finally a null value. And so this here is an embodiment of the fact that this is a recursive structure. You can see that on the inside, we've got a linked list, and then a linked list, inside a linked list, inside a linked list, inside a linked list, and finally, the entire structure is a linked list. So this is a recursive structure that you will see later in computer science. The next recursive structure we'll look at is that of binary trees. So at its core, binary trees are just a collection of nodes that store data values and pointers to other nodes. So at its core, that sounds a lot like a linked list. And it's not that they're dissimilar. However, unlike linked lists, the node in a binary tree holds pointers to 2 other nodes, or null, depending on whether or not it's pointing to an empty binary tree. So we still see that null popping up. And so a binary tree is either null, representing an empty binary tree, or it is a root node that holds pointers to a left and right subtree, both of which are binary trees. But for instance, we could have the following. So we could have the root node 1, and then it would have 2 pointers, one to the left and one to the right. And so this is a binary tree, and it's pointing somewhere. But most importantly, it has a left and a right subtree. It's pointing to binary trees below it. So the left subtree is a binary tree, and it could also hold information. So this could hold 2, and then it's going to point to a left and a right binary tree. The left binary tree might be the empty tree. The empty binary tree, I'll just mark as a line, and so this would be represented by the empty tree. And maybe the right one actually does point to another tree which holds data 3. But the left and right binary trees could be empty. On the right, we can see the same. So maybe we get, it holds data 4, and it has a left representation, but the right one, the right subtree of 4 could be empty. Whatever it looks like, it's at most pointing to 2 different subtrees, the left and the right subtree. We'll see more about binary trees later, but the general idea is the same. It's a collection of nodes storing data and with pointers to other nodes. The definition of a binary tree requires that it be recursive, because it is either an empty binary tree or a node pointing to another binary tree. And so what this tells us is that this binary tree, we keep moving out towards the leaves of the binary tree to the final ending points at the bottom of this binary tree until we reach a null or empty binary tree. So we know that we'll keep moving out the left and right subtrees until these end. And those we call leaves on that outer edge. There's certainly more to come from binary trees, but that's a first look. That's all for now. We'll see you next time.